Everyone looking at class number 28, our goal is to calculate and compare the forces of kinetic and static friction. So in our do now, it's just like a review of finding the normal force. So we have a car sitting on a flat surface. I'll do the whole free body diagram method for this one. Um, but in this case, the weight does end up being equal to the normal force. We have negative weight or negative Fg, and going up, we have the normal force. All right, there are no other forces acting on this. So the acceleration in the y direction is equal to F net over m. It's not accelerating up or down, so A is 0. F net is just normal force minus or plus negative Fg all over the mass. Multiply both sides by the mass, you get normal force equals Fg. Therefore, the normal force equals mg in this case. M is 2,000, g is 9.8. And we get something like 19,600 newtons for our normal force. All right, hold on to that, put that in our back pocket. We will use that later. So we watched a video on anti-lock brakes. I highly recommend you watch it again. It wasn't that clear, showing it in class, but definitely watch it again on your own computer. What we saw was with anti-lock brakes, the wheels continue to spin as the car stops. Without anti-lock brakes, the wheels lock up and stop rotating, causing the car to skid. So definitely watch that video and notice the difference. Anti-lock brakes, no skidding. Without anti-lock brakes, skidding. And we discussed a little bit in class, this video down here might help you a little bit. We discussed that when the wheels are spinning, this is static friction. Now, you might not think so because the wheel is moving, but the part of the wheel that touches the ground is not moving while it's in contact with the ground. The part of the wheel, and when you have with no anti-lock brakes, excuse me, and it's skidding, it's sliding across the ground, so that would be kinetic friction. Because again, the part of the wheel that touches the ground is moving. Okay, it's sliding. Why is friction a good thing while driving? Think about why is it challenging to walk or drive on ice? Friction is needed for a few things. You need friction to slow down and speed up and to turn. All right, think about if you're like driving on ice and you try to turn, it won't let you turn because there's no friction between your wheels and the road. So we've seen this graph before. I just want to kind of talk about it briefly again. When we have static friction, the force of static friction matches the applied force up until this threshold. Okay, if you recall, this threshold point here was force of static friction equals coefficient of static friction times the normal force. All right, that was that point right here. Then you have kinetic friction, it's a constant. So once the friction is kinetic, it gets lower than that threshold point, but it's a constant number. It doesn't constantly increase like static did. According to graph below, how does the force of kinetic friction compare to the force of static friction? Force of friction kinetic, and this is the important part here, is constant. It's given by this equation here, force of friction kinetic equals coefficient of kinetic friction times the normal force. And number one, the force of kinetic friction is constant. Thus, this equation can always be used to find the frictional force if the object is sliding. I think moving isn't a great word to use. I think we're going to start using the word sliding. Okay, because moving, as we saw, wheels can be moving but have static friction. A person can be moving but has static friction between their feet and the ground. So from the do now, we have the normal force is equal to 1900 newtons. Also, just so we have it on hand, the mass was 2,000 kilograms for that car. Not 200, but 2,000. So refer to the car in the do now. If the car were skidding, so no anti-lock brakes, calculate the force of friction between the tires and the road. Think static or kinetic. So it's skidding. So we said that was kinetic because the tires are sliding. So let's do kinetic friction. So we have force of friction kinetic equals coefficient of kinetic friction times the normal force. So the force of kinetic friction is what we are looking at. The coefficient of friction. We're going to look here. Rubber on asphalt, dry. All right. So we're going to use the kinetic coefficient, which is 0.67. And the normal force is 19,600 newtons. All right. So get your calculator out and see what that comes out to be. Let's see. I got mine here. 0.67 times 19,600. We're going to get 13,132 newtons. Don't worry about sig figs there. That number is just fine for us. So again, referring to the same car, now it's not skidding. What's the maximum amount of friction the tires could apply before skidding? So that's going to be static friction. We're going to use that threshold. This is that threshold, like just before it begins to skid. So that 0.85 is from the chart. And this comes out to be 16,600 newtons. All right, now looking at number 6 here, it says using A equals F net over M, find the acceleration provided by the force of friction in both cases. Then, why is the force of friction the only force needed for F net? Think about what happens to the normal force and the weight. So the normal force and the weight cancel out, but I want you to kind of think about why. Well, if we look at our free body diagram here, we have negative Fg, we have the normal force. We know that they are equal and they point in opposite directions, therefore they cancel out. The only other force acting is friction. Now someone said, well, what about the forward force that's helping it move forward? There actually is none. Okay, objects don't need a force to move forward if they're already moving, right? Newton's first law tells us that. So once an object's moving, it's going to keep moving regardless of if there's an outside force. Outside forces, or excuse me, net forces like friction or, thrust or whatever you want to call it, like, the forward force, those will change the velocity, but they're not required to maintain our velocity. So if a car is slowing down, the only net force acting on it is friction. So we have A equals F net over M. F net is going to be just our force of friction. So in this case, with anti-lock brakes, that's going to be 16,600 newtons over the mass of the car was 2,000 kilograms. And we get an acceleration of something like, I think it was like 8.3 meters per second squared, but double check my math there. Without anti-lock brakes, basically the same thing, A equals F net over M. And let's see, I think it was 13,132 newtons over 2,000 kilograms. And I think the acceleration in that case came out to be 6.6 meters per second squared. All right. So using your answer to number 6, explain why ABS is an important safety feature in cars. You'll notice with anti-lock brakes, with ABS, acceleration is greater. Therefore, you can stop quicker. All right. That's a really important safety feature. All cars have anti-lock brakes now. You can't buy a car without it, unless maybe a vintage car. All right, everybody, have a wonderful day, and I'll see you in class 29.